Welcome, welcome to Chapter 3, Unit 4, Graphs of Polynomial Functions. So let's zoom in here a little bit. Can I zoom in? There we go. And let's have a look at this stuff. So this is 3.4. Graphs of polynomial functions. So recognizing characteristics of graphs of polynomial functions. So something about polynomial functions is they are smooth and continuous. So what that means is a polynomial function would look something like this. What would not be a polynomial function is something that has a sharp turn like that. Something that has a break in it, that's not allowed. Something that comes to a point, so something like this, that's not allowed. It will have to be smooth and continuous, like a roller coaster. Nice roller coaster. So those are the characteristic graphs of a polynomial function. Now, when we use factoring to find the real zeros, remember when we talk about zeros, what we mean are the roots. It's where y equals 0. So those are x-intercepts. So we can find them by factoring, using a graph, or using technology. Now the factoring is something that we are familiar with. So let's see, we'll try it number 1. We could do a graph, or we could do technology. So let's try the factoring first. So let's see what we can do. Okay, so the first thing I notice is I could take an x out. Okay. Let's see, what else can we do? I wonder if we can break it up. Minus 4x. So let's see. This is going to be x squared minus 4 plus, no, I don't think that'll work. And you know, we will use we'll go ahead and use a graph on this one. So that makes it f of x equals x to the 4th minus 19x, and it was also minus 30x. Okay, let's have a look at what's going on here. We can zoom out some. Okay, so it looks like we're just going to be focusing here. So what is going on? Now it looks like one of our factors is x equals 0, and that happens to be the y-intercept also, because notice that there's an x in every term, so when x equals 0, y equals 0. And then also, yes, this one looks like it would have been very difficult to find. So this one has a root somewhere between 3.6 and 3.8. So remember what I said from last time, that it can have the number of roots is the same as the highest degree. So here the highest degree is 4, and we can have 4 roots. But notice we only see 2 here, right? Well, what's going on? And that's what this section is about. We're going to learn how to determine what is going on from a graph. So here you would have found to be 0, 0, and x, it was approximately, I don't know what, 3.7. So you could say 3.70. Or you could draw the graph and just kind of indicate what it's between. If you're going to factor something, it will look a lot easier than this, just to let you guys know. But factoring is what you would do. Grouping is common in polynomials. Another way we will do it in the next section is dividing polynomials. Those also become very easy. So what we're going to look at is graphs of polynomial functions. So let me go back here, and we'll do, let's see, what can we do? X to the 5th minus 45 x. Oh man, it's hard building these in your head. We'll do to the 4th, and then plus 3 x. What does that look like? Not quite 3x. Plus, we can add another term, x squared. Okay, so some of these can look really, really weird, like this one. Let me try and think of one. Here, we'll do this. 4 squared times x plus 2. Gotta get out of there. We'll get rid of this guy. Okay, here we go. We'll have a look at this one. So notice if we were to multiply all of this out, we would get something of a third degree polynomial. And what we're going to talk about here is when it goes through the axis. So do you see in this one root where it goes through the axis, and then another root where it sort of just bounces off? This is what we're going to be talking about. And factoring is easy. Factoring is good to do here because it's easiest to see the effects of the roots if it is fully factored, which is why I had such a hard time coming up with one in general form. So the behavior of whether or not it punches through the axis or just kisses it and bounces back, that's going to depend on the multiplicity. Okay. So here we're going to take this one. So, and I'm going to go and I'm going to graph this. So we'll go back up here. So we have positive 3, negative 2, and positive 1. Oh, I forgot it already. X plus 3, x minus 2, and x plus 1. X plus 3, x minus 2. We had x plus 1. I'm going to go ahead. Third root on that, and then I need to come back here and give us my x minus 3. Let me make sure that was correct. It was x plus 3. Okay, now that I've got that together, here we go. We'll stretch this out a little bit. All right, so what we're going to look at here is we're going to look at multiplicity. That term means how many times does our root occur. So notice that what we have here when we add up the powers is 3, 2, plus 1. So that's 3, 4, 5, and 6. So this is a 6th degree polynomial. It's a 6th degree polynomial. So notice that our root, x plus 3, is equivalent to x equals negative 3. And it just goes directly through that. Just punches right through that axis, crosses it, and just keeps going. And that's one root. Notice that at x equals positive 2, right here, we've got 2 of them because it's squared. Notice how it kisses and bounces right off like you would think a parabola would do. That's an even multiplicity. Now back to another odd multiplicity. Notice here when x equals negative 1, it does punch through, but it takes a little more time to get through that axis. And the way this works is when your multiplicity, and that's the power your root is 2, when your multiplicity is odd, it will go through the axis. When your multiplicity is even, it will bounce right off like you would see a parabola doing. So it'll just kiss the graph and come right off. Now, the higher the multiplicity, the more stretched out you will see that happening. So here at negative 1, when our multiplicity is 3, notice that going through the axis is a little more stretched out. So if I were to make, now let's have a look at 2. Here we go. This is our x minus 2. So when our x equals 2. Notice if I were to make that 6. So that's a multiplicity of 6. It still bounces off, kisses and bounces off. But notice that it stretches out. So it takes a longer time to do that. And it does not actually meet the axis at anywhere but that 2 point. And I will show you this. Let's find 2. Then we will zoom in. Getting close. There it is. We're going to zoom in big time. Man, that's taking a lot of zooming. And I guess that's as far as we can go. Okay. Well, as you can see, it is sitting a little bit above the x-axis. So it's not just laying on the x-axis. But since that multiplicity is higher, it does take longer to sort of rebound off the axis. So when the multiplicity, the number of times the root occurs, is even, and when the multiplicity is odd, so remember, the higher the power, the flatter the graph gets before it punches through. That's also true for evens. So the higher the power, the longer it stretches out that rebound. And another important thing is the sum of the multiplicities is equal to the degree. And that's just simply a product of multiplication because we have to multiply all these things together. So here we're going to use the graph of the function of degree 5 to identify the zeros of the function and their multiplicities. So I notice that I might have one here at 5. I'm going to say approximately 5. So that means, or that's -5. So that means it's going to be x plus 5. And notice it goes through, but it does stretch it out a little bit. So I'm going to guess that this one is 3, since it just doesn't go straight through. These two touch the graph. They just kiss the graph and bounce right off. So I've got x equals -1 and x equals 3. Here it will be x is +1. And since that just really looks like a parabola, I'm just going to guess that's squared. And here x equals -3. And that looks just like our multiplicity 4 that we had in our Desmos graph. So my function, if I asked you to find this function, it would be something along the lines of, usually you would have some multiple of a, and then it would just be all of your zeros lined up where the orders are increasing. 3 is 4. There we go. So here you would say a 0 at x equals -1 with multiplicity 2, x equals -5 with multiplicity, and you'll spell it out, with multiplicity 3, and x equals 3 with multiplicity 4. And that's what that means. So that's how we would talk about that graph. So end behavior. So we can determine end behavior just like we did in the previous section. And we can do this with a leading term because that leading term will absolutely, remember we talked about it absolutely dominating everything. So this is, we're talking about that first term, an xn, the leading term. When our leading coefficient is positive, we're talking about even degrees. So that's x squared, x to the 4th, x to the 6th, x to the 8th, anything even. Remember, both of those go up or down. They do the same thing. The end behavior of an even degree function does the same thing. So now when we look at the leading coefficient, if it is positive, remember, they're both going to go off in the positive direction, just like we learned for power functions. If the coefficient that is leading is negative, they will both go off in the negative direction, just like we learned for power functions. And the same holds for the odd degree, just like we learned for power functions. So when you have an odd degree and a positive leading coefficient, you will have them, the positives will go off positive and the negatives will go off negative. When you have a negative leading coefficient with an odd degree, The positives will go off negative, and the negatives will go off positive. And I'm talking about this. So now the relationship between degree and turning points. So of course we're interested in turning points and intercepts. Remember, turning point would be sort of like the vertex of a parabola where it goes back on itself. And remember, a polynomial of degree n will have n minus 1 turning points. So a 6th degree polynomial will have 5, at most 5. A 5th degree polynomial will have at most 4. Now let's go up here. Notice that we had 4, 5, 6, 7, 8, 9. Our degree here would have been 9. And notice that we have 1, 2, 3, 4. We have 4 turning points, which is less than 8, which is good because the most we could have had was 8. So it's okay to have less. Now, graphing polynomial functions. So one thing we're going to do is we're going to find the intercepts. We are going to check for symmetry. We will use the multiplicities to determine the behavior near the intercepts. We will look at the leading term to determine the very end behavior, and then we will use all of this information to sketch the graph. And we're going to do that with this one right here. So first we are going to check for intercepts. So when x equals -3, we have an intercept, and when x equals +5, we have an intercept. So that means it's -3, 0, and 5, 0. Now for the y-intercepts, or I mean for the when x equals 0. So for the x-intercepts, for the y-intercepts. So it's going to cross at y. I just set x equal to 0. So we get 0. So it'll cross at 0, 0. So we're going to check for symmetry. First, we will check for f of -x. So I'm going to make all my x's negative. So that's -x plus 3 squared, -x minus 5. And you know, an easier way for me to do this would be to multiply all these out. So I am going to start by doing that. So -2 x squared plus 6x plus 9 times x minus 5 will give us -2 x to the third minus 5x squared plus 6x squared minus 30x plus 9x minus 45. So let's see what we can do. So we're going to have x cubed, keep that -2, so we're going to have x cubed plus x squared minus 21x minus 45. Now when we put -x into that, -x squared minus 21 -x minus 45, we will get, remember it's an odd power, so the negative can come out front. An even power, you can drop the negative. Now this, remember, if it's going to be with respect to the y-axis, this has got to equal our original equation. This doesn't look anything like our original equation, right? So we're going to move on. And we're going to see what this looks like. And that's going to equal, I'm going to keep that -2 negative, and I'm just going to distribute the -1 inside the parentheses. So it will be negative x cubed minus x squared plus 21x plus 45. And that does not look like this function, right? These guys don't look the same at all. So it's not symmetric to the origin, so we don't have to worry about symmetry. Now what do? We're going to use the multiplicities to determine the behavior near the intercepts. So this one is even, so it will bounce off. The x minus 5 is odd, so it will go through. And it will go through pretty straight since it's a multiplicity 1. Okay, so let's start on, I guess, plotting the intercepts. So I know it's going to go through at 0, 0. I know it's going to go through at -3, 0. And I know it's going to go through at 5, 0. So now I need to determine the end behavior. So this is my function. So notice my first term is going to be when I multiply out this -2. So it's going to be -2x3. So that's an odd function. And it's a negative coefficient. So I know that as things go, I know that as my x's get more negative, my y's are now going to get more positive, and as my x's get more positive, my y's are going to get more negative. So now I'm going to determine inflection points. So remember, it just goes through right at 5. And at -3, it is just going to bounce off. So now I need to determine what my intervals are. What's positive, what's negative. So pretty much plotting points. So notice, and an easy one to use is still in this form, the -2 x plus 3 squared x minus 5. So we'll bring that over here. -2 x plus 3 squared x minus 5. So when x is between, this is -3. When x is less than -3, I'm going to test this. So it's going to be -4 plus 3 squared x, that's -4, minus 5. It's going to be -2, -1 squared, -9. So it's going to be -2 times -9. So this one's going to be positive. So I think it's going to bounce off this way. Which means that in order to travel back through the origin, let me see. This one's, yeah, y is positive here. And now I'm going to take x equals -1. So when x equals -1, x plus 3 equals 2. And when x equals -1 here, we're going to get -6. So that is, this is positive, yeah. So that when x equals, that's 4, 12 and 4. So that is still going to be positive. Okay. So now when we reach, when x is 0, what do we get? So this is going to be positive along here. So what about when x equals 0? What are we going to get, right? So that's going to give us -2, 3 squared, -5. That will give us a positive number. It's 90. So that's going to be all the way up here. So I guess that's where it's going to cross. Which means that I think it will look something like this. Yes. Do practice with these. This takes like a lot of practice. It can get really confusing. And we will do some practice with these. Okay. So using the intermediate value theorem, so there may be some times when we maybe don't know the intercepts, but we do know values that are on different sides of the axis. And of course, we can say it has to cross the axis, so it has to have 0 between those points. So what we're going to do here is we're going to build a table. So we're going to have x and y, and we know there's a 0 between 1 and 4. So I'm just going to stick with these. So when 1 equals 0, I'm sorry, that doesn't make any sense. So when x equals 1, we get f of x equals y equals, that's 1 cubed minus 5 times 1 is squared plus 3 times 1 plus 6. So that gives us 1 minus 5 plus 3 plus 6. So that gives us minus 4 plus 9, which is 9 minus 4, so that gives us 5. So now we'll look at 2. Let me see, 2 to the third minus 5 2 squared plus 3 times 2 plus 6. And that's going to give us 4, 8 minus 20 plus 6 plus 6. And this says equals -20 plus, that's 6 and 6 is 12 plus 8. So it's -20 plus +20, so that's 0. So we have a root here. So we know we have a root at x equals 2. Now it says we have 2. So let's try f of 3. And I may need my calculator for this one. Well, we know this is 9. 5 times 9 is 45, minus 45. Let me see, 3 times 3 is 9, times 3 is 27. So that is 27 plus 15. These two equal 15. So it becomes 42 minus 45. So that's going to be -3. And then we're going to have f of 4. And that's going to be 4 cubed minus 5, 4 squared, plus 3 times 4 plus 6. Now this one I will absolutely need a calculator for. I can't remember that. So 4 cubed, 64 minus, let me see, 4 squared is 16, so it's 5 times 16, plus 12 plus 6. So that becomes 64 plus 12 plus 6 is 82 minus 80 is 2. So according to the intermediate value theorem, since these two are opposite signs, I know that I'll have something cross. That's according to the intermediate value theorem. And that's actually all it asks. So when it says show that the function has at least 2 real zeros, I'm not really asking you to find those zeros. So you know that x equals 2, which is a real zero. And we can say by the intermediate value theorem, so we can say by the intermediate value theorem, and that's exactly how you can abbreviate it. That's completely common. That's probably how you'll see it abbreviated in higher level math books. So by the intermediate value theorem, we have a 0 between 3 and 4. And then you would just provide a table that shows that you know how you have a 0 between 3 and 4. So for the following exercises, we're looking at 19 through 21. Find all zeros of the polynomial function, noting multiplicities. So these ones I can go ahead and leave for in class. So I'll give you guys a minute to review them. I'm going to focus on this one since it's already factored. So the zeros of the polynomial are x equals -3, x equals half, and x equals -1. So you could say -3 has multiplicity 2, half has multiplicity 1, and -1 has multiplicity 3. And that's what we could say. All right. So for the following exercises, based on the given graph, determine the zeros of the function and note the multiplicities. So we're going to work on, we'll go with this one. So notice that we have 2 turning points. So that means that we have 3. It's a degree 3 polynomial. So we're going to have 3 zeros. So for our zeros for number 22, we have x equals -2 and x equals 2. Now notice that it goes right through the x-axis at x equals 2. So 2 will have a multiplicity of 1. And notice how it bounces off like a parabola and it doesn't spend a whole lot of time bouncing off. -2 has a multiplicity of 2. So my guess is if I were going to build something like this, it would be x plus 2 squared, x minus 2. And that is only because I have to switch these around. So notice that the -2 becomes the +2, and that's the one with the multiplicity. So use the intermediate value theorem to show that at least one zero lies between 2 and 3 for the function f of x equals x cubed minus 5x plus 1. So I'm just going to make myself a little table. Here my x is 2, here my x is 3. So when x is 2, I'm going to get 2 cubed minus 5 times 2 plus 1. So 2 times 2 is 4, times 2 is 8, minus 10 plus 1. That gives me negative 2 plus 1 gives me negative 1. Now my f of 3. That's going to equal 3 cubed minus, and I'm just going to go ahead and say 5 times 3 is 15 plus 1. So that gives me 27, because 3 times 3 is 9 times 3 is 27, minus 15 plus 1. So we really have 28 minus 15, because we added that 1 to the 27. So that is going to give us 13, positive 13. Notice that they're different signs, so by the intermediate value theorem, since f of 2 and f of 3 are opposite signs, okay, by the intermediate value, since f of 2 and f of 3 are opposite signs, we know there must be a root. A root between x equals 2 and x equals 3. All right, that sums it up for 3.4, graphs of polynomial functions. And I will see you guys in the next one.